Good afternoon, and a warm welcome to the National Conference on Intelligent Computing and Secure Technology conducted by Department of Computer Science, College of Engineering. It's truly inspiring to see so many brilliant minds gathered here to explore the latest advancements in computing and security. With great honor, I now invite Ms. Geeta S. to officially welcome our distinguished keynote speaker and esteemed guest on behalf of the College of Engineering Chengannur.
Good afternoon, distinguished guests, esteemed educators, and bright minds gathered here today. It is with great honor and enthusiasm that we welcome you all to the second day of the National Conference on Intelligent Computing and Secure Technologies, organized by College of Engineering Chengannur. Actually, by organizing this conference, what we aim is to foster an interdisciplinary collaboration, promote innovative research, and provide a comprehensive platform for the exchange of ideas on the cutting-edge developments in the realm of computing and security. The conference features keynote address from distinguished scholars and technical sessions showcasing pioneer research. Through this gathering, we aspire to inspire new perspectives, encourage thought-provoking discussions, and pave the way for transformative solutions in the field of intelligent systems and cybersecurity. I would like to extend my heartfelt gratitude to all the participants, paper presenters, and esteemed guests who have joined us today. We are privileged to have with us an exceptional keynote speaker and illustrious alumni of our institution, Sri Appu Shaji, who has made remarkable contributions to the field of computer vision and artificial intelligence. With that, I officially welcome you all to this conference and wish you an engaging and insightful experience ahead. Thank you.
So, hi everyone. I hope all of you can hear me.
Welcome and for setting the stage for today's keynote session. It is my privilege to introduce our keynote speaker, Mr. Appu Shaji, an esteemed AI researcher and entrepreneur and proud alumni of our college. Mr. Appu Shaji is the CEO and Chief Scientist at Mobius Labs, where he is making generative AI faster, cheaper, and more accessible. Previously, he was head of R&D at IU and co-founded Cyber.io. With a PhD from IIT Bombay and research experience at EPFL and Monash University, his work has had a profound impact on computer vision and multimodal AI. Today, he will share insights on recent advancements in multimodal AI, transforming how machines understand and interact with it. Please join me in welcoming Mr. Appu Shaji.
Hi everyone. I hope everyone can hear me very well.
Yes, sir.
So that's great. So it's awesome to be sort of at least virtually back to CEC and sort of give a presentation. So as mentioned, I was an alumni of this college and had really fond memories and sort of the formative years of my life. So it's a period which I really deeply enjoyed, and I wish I'm back there as a student. So let me jump into my presentation. So, and thanks a lot for the wonderful introduction. So that makes my life easier because I have a couple of slides introducing myself. So I'm from the 2002 batch. So now I feel like an ancient person. And now I'm the CEO and Chief Scientist at Mobius Labs. So a little bit about me. So again, if this is my batch, again, some of the best memories I had from batch of 2002. Here I am. Then I went on to do a PhD in IIT Bombay and a postdoc from EPFL. Started a couple of startups, and now I'm the CEO and Chief Scientist of Mobius Labs. In generally, sort of my passion is essentially making computers understand data. And multimodal data is kind of really interesting because it has different flavors in the sense that there is elements of vision, there's elements of audio processing and sort of speech processing, and there's a lot of elements of language, and ultimately there's elements of how to put everything together to reason. So before going to anything about AI, essentially, let me just say that our human brain is awesome, essentially. So I don't know whether the audio will transmit, but I'll just play a small sequence. I think this is from this Malayalam movie, Vanaprastham. So before I play this video, I just want all of you to sort of pay attention in what kind of data is processed in your brain. What kind of things are you attending? Are you looking at Mohanlal's expressions? Are you following the Kathakali Padams that is coming in? Are you following the stories elements? So I'll just play this a little bit. So I'll stop here. The main point for me is that whenever we like the amount of processing that happens in our brain in understanding data is something that has deeply or keeps on deeply fascinates me, because personally, for example, even that 5 to 10 second clip has so much of information, and our brains are really busy looking at various things. So if you're a Mohanlal fan, of course, you're looking at his expression. But if you're a Kathakali enthusiast, you're actually following the story behind that, etc. And all of these things are done in real time, essentially. So the question now is that how can we impart such skills to AI models where you have elements of vision, you have elements of audio, you have elements of language, essentially, and all together you have to combine that together and make a coherent understanding of this thing. So this is what I've been working on for years of my life. So with this Mobius Labs, I'm sort of we have brought out a few models essentially to do this effectively. So the models that we brought out, like since coming from the Kerala roots, we call these models as ANA models. So ANA models are something that is able to go and look at audiovisual data, like say videos, and understand human-like understanding of this video. And I'll get into a couple of demos things. The key features again about seeing, hearing, and understanding this images, videos, audio, and text essentially. There's one element that I'll talk later in my presentation, which is how to do this cost effective, because current AI models are quite expensive to run. You need a large series of GPUs to run. So how to make that effectively cost effective? That is also one element that I'll talk. So I'll keep my presentation again very a bit on sort of high to medium level, but if anyone wants some details about this, very happy to go a bit more deeper. So please do use a chat or something if you want to have some questions. I'm very happy to sort of go through that essentially. So here is here is a demo of the capabilities of our model. So what you're going to see is a small clip of a football match, and what you will see on the right hand side is AI's interpretation about what has actually in this small sequence. It is taking information from diverse sources. It is looking at the visuals. So it's actually looking at what play is happening. It's doing some kind of scene detection. It's kind of doing some kind of person detection, activity detection. It is correlating it with the audio track of the commentators. And finally, it's combining it together. So I'll just quickly show that video.
Semenyo's won it back on the halfway line. He's dispossessed Nakanathe. Here's Tavernier to Semenyo. Saved. Comes back out to Kleiber. It's saved again by.
So I'll just stop here. So what the AI system is able to again understand by looking at all these data sources which is available in this video is that it was a tense soccer match. The main player was someone called Antonio Semenyo. He nearly scores a goal, but he was able to be tackled by an opponent. The ball then goes to Kulver, which is one of his team member. He also tries an attempt at the goal, and then it unfortunately gets saved again, depending on which team you support. And then there is this huge atmospheric sort of thing. The fans are completely engaged and they're watching an extremely dynamic gameplay. So I'll play this again. So just to sort of see what all information the AI model is able to bring it out.
And Anton Semenyo's won it back on the halfway line. He's dispossessed Nakanathe. Here's Tavernier to Semenyo. Saved. Comes back out to Kleiber. It's saved again by.
And now I'll go to one more sequence. This is a ice hockey game, which is quite popular in Europe. So this is where not a sports event is happening, it's post-event. So it's able to actually identify this is an event of inside a game between two countries. In this case, it was Slovakia against Kazakhstan. And it is a closely contested hockey matches because it had information about the scores inside, which was embedded into the video. So the game was tied at 2 goals each after 3 periods. In ice hockey, you have three periods, not halves, but 3 periods. And the Slovakia team erupts in celebration upon scoring a goal and sliding into the net and with the puck and racing the sticks triumphantly. So this is really cool. So once we generate this, what can we further do? Because that is, again, something which is what are the applications that we can build. One of the most interesting application, at least from my perspective and where we work a lot, is on very intelligent search and discovery. So I'll go into the next example. So for example, here, what you're going to see is that we use our ANA model to basically run through around 200 hours of videos of highlights that was coming from FA Cup. And once this has been analyzed, we can now interact with the system and ask the systems questions about these videos it has seen in the past. So I'm asking it a question, show me the details of the match between Rovers versus Palace. It goes back to the database, essentially, and is able to go and pick out all these details that it has watched 12 videos between Rovers and Palace. But based on the information you are specifically asking for this match, which happened on February 25, and the score of that match is basically Palace won with 2-0. And I have video sequences, which is coming from various elements, for example. So, for example, I want to know a bit more of the match highlights video. So it goes back and goes through the data it has already extracted back and identifies these key moments. So the kickoff happens at 2 minutes, and sort of the first goal happens at 26 minutes. And then you can click and then you can go to that exact location where this happens, essentially. And also maybe something else, you want to find maybe something unrelated to the events. You want to find elements where there are places where like some kind of brands appear in this thing. So I asked it find key and powerful moments for a marketing team. It goes back and finds out all these kinds of details that say at 12 minutes, Nike was there and Mbappe. And this was shown in Mbappe's logo when he was hitting the post after dribbling past 2 defenders, for example. And let me just go further. And here is also one use case. I asked it to sort of put together some moments because I'm a big Liverpool fan, and I want to see all the great moments where Mo Salah essentially scored the goal. So it went back to all that archive things and puts up all the goals, and then specifically it also sort of clusters these things where there are goals coming and celebration at Old Trafford, where they have this rivalry with Man United, essentially. And in generally, there are applications in search. I think we saw a couple of demos. I won't go into further demos. But there are applications in education. For example, you are consuming a lot of podcasts, a lot of lectures, etc. And you as a learner want to improve. You can ask the system, okay, can you give me a quiz about multimodal AI? What kind of different models are typically used, etc. And as AI is able to go and put together new quizzes and new tutorial materials as and when. Or you can also ask it specific things. Say you want to fix your bike, and then you want to find how to sort of adjust your bike lever. You can go and ask, I want to lower my bike seat. Is this a lever? And it goes and gives an explanation essentially of, okay, no, this is not the lever. This is for quick release mechanism on your front wheel. So what you should be looking is something what you see on the bottom most things. So Now I'll go a little bit on the technical side. So before going that, if there is any questions, I can take that. Otherwise, I can go into the technical side of why multimodal AI is basically breaking into the market pretty heavily. Okay. So I assume that there's no main questions here. So maybe I can go into a little bit of details essentially. So the whole AI revolution that is happening right now is basically fueled with three major things. One is the data, especially after internet formed, and as time goes on, there's like amount of data you have to train these models are really increasing. So I see a question. So ANA model deals with videos. Yes, it deals with videos and also subset of video. For us, audio is a subset of video because audio also have an audio track, images, and also languages. But ultimately, it is built for as many modalities as possible. Video being the main place that we are trying to monetize the technology.
Sir, is it trained for all the applications or specifically for this cricket like gaming applications only?
So we try to build very general purpose models where we can take these general purpose models and we can fine tune on specific applications. So when we work with certain clients, we do fine tune for specific applications. So for example, for movies, there is a slightly different model that is required. It so happens in the generative applications, fine tuning requires less amount of effort compared to building the first model. And even with the first model, we do leverage a lot of open source models to build on top of it, essentially. But a lot of our clients, the applications is coming from the sports broadcasting area, but we do also have clients coming from, say, video broadcasters who are doing news items, who are doing certain Netflix kind of series, essentially.
But actually, our students has done many projects related to different type of models, not videos, because of the lack of GPU. Is there any open GPU available for doing the student projects?
So typically we use models from cloud instances, essentially. So we don't keep our own hardware within the company. That's one of the issues that we have, is that with larger models we need a lot of amount of GPUs. So again, we have also the same issue that buying these GPUs is very expensive. So there are services like, say, Vast AI and Rugboard, where we rent out GPUs somewhere between 50 cents to €1 per hour, essentially. And depending on the use case, we scale it up or scale it down. But getting GPUs is a hard problem. It's expensive, super expensive at this moment. But at the same time, this also opens up an opportunity to do things in low cost, because the cost is, and which I will cover in the latter part of my presentation. Because managing costs both for training and both for inference is really a need of the hour, especially because if you have to deploy AI in scale, it becomes really expensive. So compared to other applications, AI is typically 20 times to 80 times more expensive. So we just need to manage that. So and also with the student projects, I can also talk in an individual basis, and maybe can help in the algorithmic level, because that's where we put our efforts to see if we can train models and actually run these models cheaper than what is possible at this moment. So I can go. I hope I can go forward. These are the kind of the three aspects that we concentrate on. One is on the why multimodal AI is possible right now, because the data availability is pretty high. Compute GPUs is available. It's still quite expensive. And then there are algorithms which is able to train on this data, which is of very high volume. And then later, fine-tune these models essentially to get very high quality results, essentially. Um, so in generally, let's look at data. When training AI models, usually it goes through a few phases. The first phase is called pre-training, and I'll talk a little bit about pre-training. So pre-training are very good to create a model, like say like a llama or like a Quen, a model where it is quite general purpose, but for a specific task, it might not do very well, but it has, I will say, very generic general knowledge. So it has a large amount of prior knowledge, which can be later then be used to further fine tune with very high quality data. And there are different fine tuning mechanisms like, say, supervised fine tuning. RELF is real time reinforcement learning with human feedback and the loop. Then there is DPO, and there are different algorithms which are able that we utilize to fine tune this data. And then in the last 1 to 2 months, we have been using inference span compute that are models. I think most of you must have heard about models like DeepSeek, where while doing prediction, we allocate more compute to reason, is my answer correct? If my answer is on what are the things that I should be looking at, and have more steps where it more loops and more iterative loops with the aim of getting better results. And inference time compute is basically how can we shift the compute not from training side into inference side. So we can do more compute when someone asks a question. It will be slower but more accurate results, as opposed to training a large model where it has seen all possible questions, all possible interactions that someone can do, which is more expensive to do. So let me talk a little bit about how pre-training is done, and these are kind of examples to explain. So maybe for all of you can do a little bit of mental exercise. This is a text that I just cut and pasted from our college's website, and I have masked certain portions of the text. So if you can read this, essentially, can everyone just see if what text could have appeared here? So, for example, College of Engineering Chengannur was established by the government of Kerala under the aegis of something in the year something. It has been approved by some entity whose acronym is AICT and affiliated to ABJ Abdul Kalam Technology University. Ever since its inception, the college has maintained its eminence as a leading engineering college in Kerala. Being located in some town, in some district, the college has got access to all means of transport and communication. So one way of learning about things is, and I will just give the answer key. So in the first case, it was IHRD was the answer. In the second case, it was the full form of AICTC was All India Council for Technical Educations, and then it was based in Chengannur, in Alapi district, etc. So one way for us also to learn is basically go through a lot of what we call this as fill in the blank kind of questions. So we try to solve this, then we cross-check if our understanding is right. And okay, if we got Chengannur right, then that's right. But if someone has written Chengannur, then that's not correct, essentially. So with this large amount of corpus of data, what we can do is create these kinds of filling the blank questions by masking certain elements out. So for example, this is another text. We can mask out random portions of this text and ask the machine learning algorithms or the AI algorithms to guess what is it. And the assumption is that if you do a lot of these kinds of filling the blanks or mask questions, AI is able to understand and is starting to model these these knowledge, essentially. So this is how almost majority of all these models are right now trained initially, like for GPT-4 or cloud or everything. They go through large corpus of data sets. In the pre-training phase, they mask out, they take random text from internet, mask out random portions, and make the model guess it. By doing it trillions of times in trillions of data sets with these large models, and understanding emerges how to fill in these things. So there are elements, for example, it will automatically learn elements of grammar. It will automatically learn elements of um, elements of relationship between objects, etc., because it has basically done this exercise millions and millions and millions of times in large corpus. So for images, it does very similar trick. For example, it tries to mask out certain regions of the images and guess. And sometimes you have pairs where there is an image and there is a caption attached to it, and maybe a part of the caption is masked out, and it tries to guess. And by doing it again in such a large scale, it is able to sort of have an understanding of this data. And the next portion is fine tuning. And for fine tuning, you need more precise data. For example, what is happening inside inside a video, inside a text, etc. These are more objective. Objective answers. So maybe I can go to one particular data set. This is coming from Hugging Face for video. So I'll just take testing travel. So this is some video about in the
What's
road.
up?
Someone has manually annotated all these details. In this video, there were these characters. There was a traveler. There was a Michelangelo's Moses. There was Jesus involved, and these were also the breakup of introduction of breakup of scenes. There are multiple scenes involved. So scene 1 is introduction to Rome. Scene 2 is Michelangelo's statue of Moses, etc. So you have all these elements that's like in the first stages created either by humans. Recently, because now AI models are becoming quite powerful, we can create synthetic data, which is and then cross-check if the synthetic data quality is high, and then use that for training. So this is typically how training process is done. As someone who believes a lot in open source, we usually share our models in open source very freely. We get with teams sort of collaborating with us, and with the entire community, which is also producing data essentially. So which is really cool. Now I'll talk a little bit about the algorithms. I don't know how much of you are know about transformers, etc. So then I can go into the details. So I'm just or should I make it a bit more entry level understanding of transformers?
Please explain it, sir. Transformer model is we are doing projects like that.
Okay. So cool. So then I'll sort of go in the top to mid level kind of thing. But before going to let me just jump into the transformers. So this is a very interesting website. I can share the slides later with these links, essentially, where transformer models has been sort of visualized very well. So what you see here is a small transformer model. This was done by Kaparti. This nano GPT model. It is a very small model. It's essentially only 85,584 parameters. But typically, all these models are the basic underlying principles are the same. The scale is just different. Some models have, say, 70 billion parameters. Some models have, say, especially these big companies like OpenAI's models have like 2 trillion parameters, essentially. But this is a small model by capacity. So what you will see essentially is like the layers that you see. This is the input layer. This is the output layer. And I'll talk a little bit about the input layer in the next slide. And what you see internally, I think it has this, like this from here onwards, like you have these 3 blocks essentially of what we call as a transformer layers. So transformer layers is basically this particular architecture. I won't go too much into the math, but essentially what it does is that it has three values. Let me see. You have three big tensors essentially. You have one tensor called the Curie tensors, the Q weights. You have another tensor called key weights, and then you have something called as the value weights, the V biases and V weights essentially. So think about a ordinary sort of a hash table or a dictionary. So you want to find the meaning of, say, a word like attention. So then you have that is your query, and this is, and then you go to the index page, and then you find the exact place where this thing is happening. That is your the key page, and then exact description about what is happening that you can think about as the value thing. But in the case of transform models, these are all numbers, learned numbers. So initially, these transformers is initialized as random weights. Over time, it will generate these the Q matrices and the K matrices and V matrices, which is kind of the information of the world that it has seen. So go back to the data example that I gave. A lot of fill in the blanks examples that it does. Every time it sees the fill in the blank example, it will note down in the models essentially what are the kind of the good informations that I've seen which can probably help me. Then it goes through this process of back propagation where every time that it tries to guess whether it's the right answer, if it's not the right answer, then it will go and update the weights. If it's a correct answer, it'll keep the weights like this. So by training it out on, again, millions and trillions of this data, you will get very good representation of Curie values and key matrices. And there are other elements which is mostly for computational reasons, convergence reasons, etc. I think it's a short session, so I can't go into too much details here. But these are all kind of extremely important layers that is required. At the end, what happens is that you multiply the Curie and the key values, and then later with the value matrix. What it will tell is that at the end of each layer, it will give you a part of the network where it needs to attend to. Because I'm asking a question, where is Chengannur? Then it should not be thinking about Europe, or it should not be thinking about North America. It should be thinking about India, Kerala specific. So there's a part of data stream that it needs to be attending to. So depending on the query, only a subset of these layers will get activated. And one of the things that has historically worked very well is that the more number of these transformer layers you stack up, the level of understanding becomes much more granular and much more stronger. So for larger companies, for example, till let's say 2024, how they got the values is or how they get more bang for the buck is stacking up larger and larger models. So more information could be modeled into these transformer methods essentially. Now I'll talk a little bit about how the input is given, which is also an interesting element, which is computers understands only numbers. So then you have to tokenize any input that you have essentially. So I go into one example here. So I want to communicate to the machine about something. So tell me what all subjects or what all topics should I cover in this presentation. So first, what the input does is that it puts certain special tags. For example, in this case, for most chat applications, you have two kinds of prompt. You have a system prompt, which is a very generic information to the model, and you have a user or instruction from the thing. So you have certain tags that is being generated essentially. Now, each of these, like finally you get a text like this, then it will chunk the text into small pieces. You can think about this as words, but this is not really exactly words, because some of these things like are multiple, covers multiple regions, for example. So each color that you see is a token in this case. So I am start is one token, system is another token, I am sim, and each of them will be assigned a number. And there are different kinds of tokenizers available. So let me talk. Let me look at meta things. So let me just, what kind of information should I cover in this presentation to students of College of Engineering Chengannur? So you can see that this is being converted into these numbers. The reason I'm talking about tokenizer in this particular presentation is that how do we go from text to handle more modalities like images or videos? Because for transformers, the input is a tokenizer. So for multimodalities, we can also convert images, videos, or even audio streams into these kinds of numbers. So in images, we use something called as vision encoders. So this is again a small transformer model. I won't go into too much details because it's a bit more involved, but fundamentally a patch of images will be transferred into a set of numbers like this. So then we have a way of giving rich input, which is covering over all the modalities, whether it is image, whether it is video, whether it is whether it text, into the transformer models. So this is one of the advantages with this transformer-based architecture, where it is we can have the same base architecture and we can model different modalities. Yeah, and finally, last but not the least, I won't go too much into the details. I think everyone is kind of well aware. One of the basic driving forces of AI right now is essentially compute. So there's an interesting video from NVIDIA by the Mythbusters guys, which shows the difference between a compute which is done by a CPU versus GPU. So for CPU, everything is doing, each data item is being processed in a sequential one by one way. So it's a bit like making it.
3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 10.0.
when we hit this trigger on this thing,
So with GPUs, I will go a little bit more faster. All the data that is coming, or a chunk of the data that is coming, can be processed simultaneously, and that's why it is fast. And some of these recent GPUs, say the Hooper machines and the Blackwell ones, has much more tensor cores. Each tensor core can handle a lot of this data, and we can do massive amount of compute within each machine.
reach its target, hopefully.
So
Painting demonstration.
Yep.
And 10, 9,
8,
7, 6, 5, 4, 3, 2, 1.
So you have this amazing capability to do everything parallelly.
All right, I introduced you.
So with these three elements, which is compute, data, and algorithms, right now, the amount of things that we can model, especially with AI systems, is really, really massive. And there's a lot of work in all these aspects which is coming in. One is how can we again get much better input model. So that in that case, we work a lot on tokenizers, how to get much more better learning capabilities for transformers. Then we work in this individual layers that which I sort of briefly alluded in the few minutes back. And there is also work on how the training data sets is being done. now in the last 10 minutes, and again, this will, my slides are a bit more involved because it's a bit more technically involved, but I will try to give a gist essentially on the compute side. Because one of the issue that we have right now, I think the question was was also on the same line, that the compute costs are like crazily high. So how can we do all of these processing, whether it's understanding videos or creating videos, in a cost-effective way? So this is one element where my team basically works quite hard, and we have some fundamental breakthroughs that was created here. So one of the issues that we have is, for example, if you want to run a model like Llama 70B billion, and we run this in a cloud-based GPU that we get it from a system like a Vast AI or a Amazon or Oracle instance. To run 70 billion in a cloud instances, it costs us around, we need at least 4 A100 GPUs, and this will cost us around 14,000 euros a month, which is very, very high, essentially. And for us as a business, even if you make sure each of these GPU time is basically utilized, amount of money that we can make is by selling this technology is only 10,000. So in effect, we are basically throwing money away, like 4,000 euros is being lost every month, essentially. So what we want to do is we want to make the algorithms super efficient, so we can run the same model with very, very high quality, but at the same time at a fraction of the cost. And how we do this is basically few things. And I will talk about only a couple of these things in the next 10 minutes. One is we design models which are smaller. One thing that is that to train these models, you need large architectures, but we can take these large architectures, and there's a process called distillation where we can take what the large model has learned into a smaller model much effectively. Then there is other methods called quantization, which is what I'm going to talk about, where we can make an existing model smaller, again 4 to 8 times smaller, by running it on low precision. I'll talk a little bit about that in the next 10 minutes. Then there are elements like fast inferences, because all of these GPUs have certain compute layers, and if you utilize it very well, then you can actually run these models faster. And for that, we have to write certain things like CUDA and Triton kernels, which makes these models run really fast. But at the same time, these compute optimizations that we do should not reduce the quality of these models. So we want the same quality of these models such that and at the same time make sure the compute is like 10 times to 15 times reduced. Then only then for us it makes sense, or for any sort of AI field it makes sense commercially, especially because of the cost of the compute. So it is this intersection that we work a lot on, how to bring this amazing capability to understand videos, audio, and everything, but at the same time essentially do this in a scalable and cost-effective way. So I'll talk a little bit about the quantization work. I'll give you a gist about how quantization really work, and then a little bit of the techniques that we use. So some of these are quite involved. So if you don't follow, happy to sort of maybe tone it down a little bit more and then explain it further in a later session. But just I think I briefly talked about this particular slide. That the model that we have, especially the commercial models, have millions and billions of parameters. So, for example, a model like Llama 270 billion, it requires 140 gigabytes of GPU memory, and it won't fit into a 180 gigabytes. And to train it, actually, you need to double it. So you need at least 4 A100 GPUs to run it. And this is super, super expensive. This becomes for a small startup like us, it is quite unaffordable. You need to be a Google or you need to be a Facebook to afford that, essentially. And things are, for training, it's even worse, essentially. So in the transformer-based models where we went through, most of the weights are in what we call as linear layers. So these are big tensors essentially. And there is some element, and the compute is in linear layers and attention. The attention layer itself doesn't take too much of memory in GPU. So the idea is that typically these GPUs are designed to pack what we call as floating point 32 or floating point 16 numbers. Just give you a little bit of what these are. Yeah, I don't have that slide here. So floating point 16, roughly you need 16 different numbers to basically store FP16. Usually for FP16, you allocate around 8-bit for the exponent term and 8-bit for Mandelsat term, and then there are another couple of other data formats. But can we get the same answer by doing the compute in, say, floating point 4 or in 4, or even as little as, say, 2-bit or 1-bit. In 1-bit, it's basically a binary matrix. So each of these weight, instead of it being this large floating point number, can we compress that essentially to as small a number as possible? What we found is that till 4-bit, we can actually keep the quality extremely high. And we have done also some work where we actually make the number of bits as low as 1-bit. So it's really binary. So each of these big numbers is basically floating point numbers will become a 0 or 1. So this is how to approximate this large model with a small amount of thing. So in generally, there are two things that we can quantize. We can quantize the weights and quantize the activations. Activation is the final results of the thing. Activations will also result in faster inference of the compute point things. In generally, transformers-based quantization allows us to be much cheaper and much faster. So again, let's look at the transformer model a bit more in the things. So you have this query key value matrices. These are all the linear layers. And there is something called as rotary embedding, but we'll go back into this. And there is a self-attention going into down projection into MLP block. Most of this heavy matrix multiplication is compute is in this heavy matrix multiplication that happens in this QKV layer, essentially. So what we do is that we build these operators like quantization operator. So this is a quantization in 4. So you have a floating point 16 number metric tensor with different numbers, say 1.5, 30, 2.3, negative 1.3, etc. Instead of keeping this, can we actually store this as 2, which is kind of rounded up to 1.5, 30 to 15, 3, 1, and etc. Just now rounding up or rounding down won't work because there's a huge loss of accuracy. Because what you really want is the relationship to the numbers, and certain weights are really high and certain weights are very low. So the scale is a bit skewed. So the question that we ask ourselves is that how to maintain very high quality output. Whether again the goal is to take this XP16 tensor into a 4-bit tensor, but at the same time making sure that the quality is not suffering, and also the processing time is pretty fast, and the contents and the contents itself should not require expensive hardware because we're quantization because we can't afford this hardware. So these are the kind of things. So typically there are a few processes that is being done. The process that we do is weight quantization, where we write the operation that is happening is matrix multiplication between the weights and the activation plus a bias. Can we essentially have a quantized weights WQ, whereas the size of WQ is less than NW. So typically we keep 2 extra parameters, and these 2 extra parameters are what we call as the 0 point. 0 point is like if you have numbers for from minus 16 to 16, the dive quantization 0 point will be 0, but it need not be 0. You can keep the place where it just crosses at 0 at 2 or 3. So this is a parameter that we can adjust. And there is another parameter called the scale. So we have this algorithm called HQQ that we invented, which is able to do this with certain minimization techniques. I won't go into much more detail, but in general, the advantage is that we can actually quantize this, say, a llama model of 70 billion model up to 3-bit with less than 0.3% 0.3% loss of accuracy. And there is also two things that we also work on. Essentially, you have this something called the memory bound compute and the compute bound optimization. Memory bound optimization happens when you have low amount of data, so you're just asking it one question. You can't parallelize it very well. In this case, you have a different kind of optimization, but you have a batch scenario. You have like thousands of data to be processed simultaneously. Then you have a compute bound optimization. I think I won't have time to go through it because I only have one more minute left. So I will just try to go and essentially just give a summary for my presentation. What we are able to do is that we were able to bring the cost of multimodal model down by a factor of 8 to 9x using these methodologies. And I will talk a little bit about what I think will be coming in this field of generative AI. 2025, I considered it to be an age of agents, where you have LLMs with certain abilities. For example, ability to sort of understand an image, or to go and check the weather, or you have the ability to sort of understand a certain phrase. And these things which are some it's very good for certain one task. Broadly, the community is now calling it as agents. And these agents, different agents with unique skills, can interact with each other to make much better output. So this is a little bit like, maybe a metaphor will be like how a human body is working. Your eyes to see, fingers to gesture and to pick up objects, etc. You have different functionalities, but as a unique entity, we are using all the functionalities from these different parts of the body to actually do something. Reasoning is also one important element that people are working really hard on. How to think long and actually get into much more better results. So this is an area which is on active research at this moment. Actions are pretty important in the sense that you are now AI models which is capable, for example, look at what is happening in the screen, where to click, what action to basically take next, like what is once you process these data, how should it move, essentially. I will say agents, reasoning, and actions are kind of interdisciplinary skill where one will inform the other. And this is going to be super interesting when we actually put these models into devices like robots and drones and everything, where you can actually have the sort of the ability to move around and make certain decisions. The other ones, for example, now we will see a lot of AI models being trained by each other. Maybe in the next year, this presentation will be one AI model sort of instructing a set of new AI models on how to do that, essentially. But at the same time, with AI, there are all sort of alignment of AI models are super interesting. Again, I will not go too much into the details, but this is a huge field by itself. And I will just start with this thought. One of the reasons, for example, personally, why I started working on this field is that I was always reading Isaac Asimov's and sort of a lot of sci-fi book when I was young. And I always had this thought that robots that you see in these books are almost very autonomous beings, essentially. It's doing all the farming, it's doing all the industrial jobs. It's using a lot of these skills, like it's using cameras, it's using the machinery, it is using direction ability. For a long period of my life, I thought this is just sci-fi. This won't be realized in my lifetime. This is here right now. So this is an interesting or probably the most interesting period of AIs, and it's really a golden age. So with that thought, and I think I'm really waiting for the amazing things you folks can do with this thing, because you probably will be entering into a world where technology's ability is sort of endless, and you can do so much cool stuff with it. Thank you very much.
So if anyone have any more extras,
I could not hear you.
thank you, Mr. for taking time to share your experience with us today. Your insights in the multimodal AI and applications are really enlightening. It was an honor to have you, and we deeply appreciate your valuable time and knowledge. It was a privilege to have you with us, and we look forward to following your continued innovations in this field. Thank you once again.
Thanks a lot, and it's always a pleasure to sort of talk to folk in CEC. So all the best for everyone. Thank you very much.
Thank you, sir.
Bye.
With that inspiring start, I am delighted to welcome you all to the day 2 of the International Conference on Intelligent Computing Technologies. As we move forward, we will now begin the sessions with each team will showcase their research and contributions. I encourage all participants to actively engage, ask questions, and exchange ideas as we dive into these innovative studies. All participants are requested to join their concerned meeting link for the presentation. Let's continue this journey of learning and discovery together, wishing all presenters the very best. Thank you.